In the conceptual video on vectors, it ended with us introducing the idea that you could find the components of a vector. So let's say, for instance, I have a vector that looks like this. You should be able to find what we call the horizontal and vertical components of that. And the way to draw that is to think of this thing as existing inside a rectangle. So I'm going to picture this as being one side of the rectangle and this as being the other side of the rectangle. And of course you could kind of picture this making a box. This would be the vertical component, this would be the horizontal component. I'm going to actually just call this V for, it's probably a velocity, that's mostly what we're going to be doing. What we would call these are Vy for the vertical component and Vx for the horizontal component. Now the way that you find these components is some very simple trigonometry. If you can imagine this red vector, I could draw, this is one side of a rectangle, so the other side of that rectangle has got to be equal, okay, and parallel. And so these actually make a right triangle out of this. And we have an angle here. So using our trigonometry, if this is our hypotenuse, then our horizontal component, we can write an expression that looks like this, because the horizontal component is our adjacent. So we know that the cosine of any angle is the adjacent over the hypotenuse, but in this case that's Vx over V. And if I solve this for Vx, I wind up that my horizontal component is equal to V, the original magnitude of the vector, times the cosine of the angle. It's very important that this angle be the angle that it makes with the x-axis. If you can't use this angle and use this result. For the vertical, it's a very similar process. The sine of the angle is equal to the opposite, which in this case is exactly equivalent to Vy over the hypotenuse. Solving for that vertical component, we get Vy equals V sine theta. If you're given a vector that is not vertical or horizontal to begin with, finding its components is simply a matter of plugging the numbers into this relationship over here. Let's do a very quick example. All right, we have a velocity vector. Let's say it's a plane flying 200 kilometers per hour, and it's kind of headed in the northwesterly quadrant. And what we need to find is how fast is it moving to the west, which in this case is left, and how fast is it moving north. So let's draw our vector components. We have a component that moves this way, and we also have a component that moves this way, but typically I actually make it into a right triangle. I just find that more helpful. It doesn't really matter how you go about this, but I've seen what works over the years. So this is Vy, and this is Vx. All right, and now we just have to use our little formulas. Vx is V, which is the magnitude of our velocity vector, times the cosine of the angle. And that's going to give us 100 kilometers per hour. Now we have to be careful here because this component is still a vector, so I need to give it a direction, and it's pointing west. Now we will be doing these also where it's just in a coordinate system. To the left would be negative. Instead of writing 100 kilometers per hour to the west, I might just write negative 100 kilometers per hour. In our next video, when we talk about addition of vectors, you'll see why that's kind of important. And then Vy equals V, which again is 200 kilometers per hour, but this time times the sine of 60, which will give us 173 kilometers per hour, and it's pointing north. There we go. That's how you find the components of vectors. Now, what if you had the components of vectors and you wanted to know the vector itself? Well, that doesn't get any easier. If I had vector components, and say for instance, I'll call it Vx is 30 meters per second, and Vy is 40 meters per second. That constructed Vx would look like this. Vy would look a little bit longer. So V itself would be the line that connects the tip of this one to the tail of this one, the one that completes the right triangle. But what we'd like to know is V and the angle. And the right triangle part works out really well because you could just use the Pythagorean theorem. And I happen to know, the 3s, 4s, and 5 is a perfect triangle. So if this is 30 squared plus 40 squared, and you take the square root of that, gives me 50. I'm skipping the algebra so we don't have to sit here and wade through it. And then if I wanted to find the angles, since I know Vy and Vx are my opposite and adjacent sides, that means the tangent of that angle is Vy over Vx. And therefore, the angle itself is the inverse tangent of those values. And if I plug the numbers in this case, I will get 53 degrees for my angle. So now you know how to take a vector and break it into its components. And down here you saw how to reassemble a vector from its components back into the original vector. Both important skills.